Good morning, everyone. I'm Rahul Chowdhury, and welcome to our Operating Systems course. Today, we're diving into one of the most fundamental aspects of operating systems process management. This is a crucial topic that forms the backbone of how modern computers handle multiple tasks simultaneously. Let's start with our main topic, process management. This isn't just a theoretical concept. It's something your computer is doing right now as you run your browser, text editor, and other applications all at the same time. Process management is truly a core function of operating systems. Think of it as the conductor of an orchestra. It coordinates all the different programs running on your system to ensure they work together harmoniously. As we can see here, process management handles three critical responsibilities. First, it manages the entire life cycle of processes, from creation when you launch a program, through execution as it runs, to termination when it completes. Second, it controls how system resources like CPU time and memory are allocated to different processes. And third, it handles scheduling, deciding which process gets to run when. Understanding these concepts is essential because they directly impact system performance and stability. A well-designed process management system ensures your computer runs smoothly even when handling dozens of applications simultaneously. Over the next few pages, we'll explore the differences between processes and threads, learn about context switching, examine concurrency challenges, and see practical examples of when to use different approaches. Now that we've introduced the process management section, let's dive into one of the most fundamental distinctions you'll need to understand in operating systems. Today, we're examining the core differences between processes and threads, two concepts that are often confused but serve very different purposes in system design. Let's start with processes. Think of a process as a completely independent execution unit. Each process has its own separate memory space, which means it's isolated from other processes. This isolation provides security and stability. If one process crashes, it won't directly affect others. Threads, on the other hand, are much more lightweight. They're execution units that exist within a process. The key difference is that threads share the process memory space. This makes them much faster to create and allows for efficient communication between threads, but it also means they're less isolated. Here's the key insight to remember. Processes prioritize isolation and stability, while threads prioritize efficiency and shared resources. This fundamental trade-off will guide many of the design decisions we'll explore throughout this course. Now that we understand the fundamental differences between processes and threads, let's dive into a crucial mechanism that makes multitasking possible: context switching. Context switching is the foundation of how modern operating systems can run multiple processes seemingly simultaneously on a single CPU core. At its core, context switching is the CPU mechanism that saves the current process state and loads another process state. Think of it like bookmarking your place in one book, putting it down, picking up another book, and continuing from where you left off. Let's examine the key aspects that make context switching work effectively. During state saving, the system must preserve CPU registers, the program counter showing where execution stopped, and memory management information. This ensures the process can resume exactly where it left off. Time overhead is a critical consideration. Thread switching within the same process is much faster because threads share memory space, while process switching requires more work to change memory contexts. The system impact is profound. Context switching enables true multitasking and determines overall system responsiveness. Without efficient context switching, your computer couldn't run multiple applications smoothly. This mechanism directly builds on the process versus thread concepts we just covered, showing why thread switching offers performance advantages in multitasking scenarios. Now let's dive deeper into concurrency in operating systems, which directly builds on the context switching concepts we just explored. Concurrency is a fundamental concept that allows multiple tasks to make progress simultaneously, creating the illusion that many things are happening at once. The key insight here is making progress simultaneously. This doesn't necessarily mean tasks execute at exactly the same instant, but rather that they all advance toward completion in an overlapping manner. On single-core systems, concurrency is achieved through time slicing. The CPU rapidly switches between tasks, giving each a small time slice to execute. This creates the appearance of simultaneous execution. Multi-core systems take this further by enabling true parallelism. Multiple tasks can literally execute at the same time on different CPU cores, not just appearing to do so. However, with multiple tasks accessing shared resources, synchronization becomes crucial to avoid conflicts and ensure data consistency. This is where mechanisms like locks and semaphores come into play. The benefits are substantial. Improved throughput means more work gets done in less time, and better resource utilization ensures we're making the most of our system's capabilities. This foundation will be essential as we move into visualizing these process management concepts next. Now that we've seen the CPU utilization graphs and how the system manages resources, let's move into practical decision-making. This is where theory meets real-world application, understanding when threading actually makes sense for your programs. Today, we'll explore practical guidelines for when to use threads. This isn't just about knowing how threads work. It's about making smart architectural decisions in your software projects. Threading shines in several key scenarios. First, I/O bound operations. When your program is waiting for file reads, network requests, or database queries, threads let other parts of your application continue working. Second, UI responsiveness. Threads prevent your interface from freezing during long operations. And third, producer-consumer scenarios where one thread generates data while another processes it. But threading isn't always the answer. For simple sequential tasks that naturally run one after another, threads add unnecessary complexity. When synchronization costs outweigh the benefits, like when threads spend more time waiting for locks than doing actual work, you're better off with a simpler approach. The key is always weighing complexity against benefits. Ask yourself, does the performance gain justify the added difficulty in debugging and maintaining thread-safe code? Consider your team's experience with concurrent programming, and remember that premature optimization can create more problems than it solves. These guidelines will help you make informed decisions about threading in your projects. In our final section, we'll test your understanding of everything we've covered about process management.